Well, let's begin. I know there's a few others who'll join us in a minute. We didn't leave off here, but I wanted to start off the continuation here because I think that it's at this point where the difference between the optimal weight, optimal importance density that we landed on last time, after I took you through all that math that hopefully wasn't too dry, and the one that we knew to begin with, that we really want to sample from the posterior. I think I may have pointed you in the wrong direction as to why those two are different, and yet they're both optimal. And I think it might come down to the fact that the posterior, if we were to sample from the posterior, remember the posterior is, depending on how you express it, one of the posterior, I guess, in some respects that we're really interested in, is the joint posterior. And it's conditioned on the measurements all the way to time in. And yet we're restricting ourselves in the importance density so that we want to advance the particles forward in time at each time step without having to regenerate the past trajectories of those particles. So we're not recreating the entire trajectories for computational reasons, but we've partitioned this, this density that could be anything in such a way that we can generate the particles recursively. And that's why we went from n to n minus 1. And I think as soon as you make that decision, they're going to be generating the particles recursively, then you really can no longer sample from this, because if we were sampling from this, then the entire trajectory, including the state at time in, would have to depend on the measurements from 0 all the way to time in. And when we do this partitioning, the past can't depend on n. It can only depend on the measurements from 0 to n minus 1. So when we lose that ability to condition the past trajectories on the measurement at time in, then we end up with something else that is defined as optimal, because it's optimal subject to this constraint. Whereas before, if we said this is optimal, we weren't subjecting ourselves to that constraint that we're advancing the particles forward in time and computing them recursively. So I think that may have been the heart of the distinction. For me, it's terribly confusing when I'm reading the papers or reading the books about this particular topic. They don't even go through all the equations that I took you through to arrive at the optimal importance density, much less draw a distinction between that and just having the posterior as your importance density. So I've had to puzzle this out myself, and I think I'm right, but obviously my understanding is new, and I had that thought in preparing for this lecture. So I think this is the main reason why we end up with two importance densities. One is subject to this constraint, and one is not.
Was that difference thinking that at each step you're just looking at where all the particles currently are versus looking at, so like on the graphs that we were looking at where you have all the green lines of your particle trajectories, obviously that's over time, but at the current moment you're just looking at a vertical slice of where each one of those are, versus looking at the path that particle took to get there and comparing it to how probable of a path that was, that we're considering all of those examples over the history versus just the current ones.
That was such a long sentence. I didn't quite catch okay. What the question was. I understood a lot of what you were saying, but I missed the question. I guess one way of looking at it is, we say both of these are optimal, but this is for the entire trajectory. Whereas this is really looking at what's the importance density if we're just trying to figure out what the particles are going to be at time in, given that we've already generated the trajectories from 0 to n minus 1. So that's a big difference between these two. And this one, we're really constraining it where we're moving it forward in time. And when we're moving it forward in time, when we're generating, for example, figuring out what the density should be for generating the state x of n, we're not considering what the measurement y of n+1 is going to be. We are only considering the past from 0 up through the present, but we're not considering the future. Whereas when we're generating this, we're generating an entire trajectory, then technically the state at time 0, the part of that trajectory that occurs at time 0, depends on the measurement at time n. So if we're doing this really optimally the way we started off when we were trying to do the Monte Carlo integration to begin with, we said, look, we want to draw from this distribution, but we can't. Well, even if we could, there's a problem that this is not recursive. And so if we constrain ourselves to something that's recursive for importance density, and we define it as optimal if it's minimizing the variance of the weights, it turns out that doesn't mean, as I had expected when I heard optimal, and I heard variance, we're going to try to minimize and the variance is 0, I thought, well, the weights are all constant if the variance is 0. But it turns out that's not true, because we still aren't doing this perfectly, because we're constraining ourselves to advancing the particles forward from where they were and retaining their past trajectory. We're not giving ourselves the latitude of going back and recreating the entire trajectory now, given all the measurements from 0 to n. So I think that's the distinction, and I think last time I don't think I fully understood that, so I was probably pointing at the wrong things.
Yeah. So yeah, I mean the weight update equation. If you were sampling from the posterior, that's the only way you'd have constant weights.
Correct.
Your numerator and your denominator cancel.
Yeah, that's right, because the ratio of the two. That's exactly right. Yeah.
So, is there ever a case when we don't want to use prior as the importance density?
Yes. Yeah, well, actually, we're going to see some examples. Hopefully, if we have time, I'll keep a close eye so I don't keep you guys here too late. But yeah, I'm hoping that we're going to see some examples in just a few minutes, actually, where sometimes you can do far better than using that. And I'll try to tell you how to think about it. So, well, we already had a clue in the homework presentation of Ethan, where we had prior knowledge that was really good and a really lousy measurement. In that case, it turned out the prior was great from the standpoint of not having to resample all the time, not pushing the particles out to places where they really shouldn't be. In that case, the knowledge of the dynamics was really good. A lot of the examples that I generate, I'm often thinking how good the measurements are, but the nice thing about that example is you had really good knowledge of the dynamics, but we had a really lousy measurement. And in that case, this turned out to be a good choice. I'm sorry, I'm not pointing to the right thing. Choosing the prior turned out to be a good choice, because conditioning on both the state of time n-1 and y of n, this y of n wouldn't have contributed much. You know, his, in that case, the prior was probably pretty close to what's optimal. But if the measurement had been far better and the process knowledge, the process model was conveying much less knowledge, the prior knowledge was much worse, where really the important element of these two was the measurement, then it turns out we would have seen resampling all the time, as we saw in some of the other examples, apparently due to a coding error, but still, the point's the same. So, where I was going to lead you is how do you do this in practice? So we say, okay, let's say we accept that this is the optimal importance density. We're like, yes, that's what we want to use. We're going to restrict ourselves to advancing the particles forward from where they were. We're going to retain their past, and we want to do it optimally. So we want to use this thing. But now, what is that thing exactly? I mean, we can state what it is. It's the PDF of the state conditioned on what the state was at time n-1 and the current measurement. But how do we draw particles from it, and how do we evaluate it numerically? You've got two challenges, and it's not obvious how you do either one. To evaluate it numerically, again, we've got this integral that I left you with, I think, last time, where we can express this in terms of the likelihood, which we've got a good handle on, and the prior that comes from the process model. You know how to generate both of those, especially when you've got additive noise. But in general, how do we evaluate this integral efficiently without doing another Monte Carlo just to evaluate the integral for every single particle at every time step? I mean, Despite Andy's great skills with code optimization, even that's going to slow him down. You don't want to do that, I don't think. And there's not usually a closed form solution. So what do you do? Well, one of the things that you can do is kind of go back to how people used to do things before particle filters were around and computation was cheap, and basically do an extended Kalman filter or an incented Kalman filter that's based on this idea of a local linearization. And don't try it with Ethan's model with that severe nonlinearity, but with some models we can do this. And there's a couple of different ways of doing it. You know, Taylor series approximation is kind of one way of thinking about it. But let's suppose we've got a linear measurement model. I'm not going to restrict us to a linear process model. The process model can still be nonlinear. But let's say we've got a linear measurement model, just for a moment. And I'll show you how we can approximate a nonlinear measurement model as a linear one in a few minutes. So we've got a linear measurement model, and you know everything is still defined. We've got additive process noise with zero mean and some covariance matrix that could change over time. Same thing with a measurement model. It's additive noise, some covariance matrix. I've got them normally distributed in this case. And they're IID noise processes. Covariance matrices, of course, are positive definite. This is nonlinear, but we've still got additive noise. So it's a much less general model than what we've been working with the particle filters, and even than some of the examples you guys have been creating or working with. So it turns out, I'm not going to quite take you through the math yet because it's a lot of math, and we'll be going through this math basically when we talk about the Kalman filter. These are basically the linear Kalman filter recursions. When we switch over to our textbook, I'll take you through and show you where all these equations come from. It's a little bit different than the linear Kalman filter recursions because we've got this nonlinear process model with additive noise. So it's a slight generalization of the linear Kalman filter, but it's pretty close. So after a lot of math, and again, I'm not going to quite take you through it, but you've got the reference there, we end up with the optimal importance density ends up being normally distributed with a mean equal to the estimate of the state, and this ends up being the filtered, so-called filtered estimate of the state from the Kalman filter recursions, and with the filtered state error covariance matrix. And that's something we can draw from. If we know the mean and we know the covariance, you can call that PDF function, or the random number generator, and feed it that matrix and that mean, and it will give you random numbers according to that distribution. So this is something that we can finally draw samples from. And the other thing we needed for the weight update equation was this, and that ends up being normally distributed with the estimate of the measurement. I know it's a little bit weird to be thinking about a measurement of an estimate, or I'm sorry, an estimate of a measurement because you have the measurement. Why would you want to estimate it? But it's one of the things you get from the Kalman filter, and it turns out to be a really good tool for figuring out whether you've done a good job as an engineer in tuning your tracker. In fact, your single best tool, it turns out from these techniques, is going to be this estimate of the measurements and how that compares to your actual measurements. If you're doing a great job tracking, I'll just give you the punchline right now since some of you are working on this for the next homework assignment. If you're doing a great job tracking and you look at the difference between your measurement and the estimate of your measurement, which is basically just feeding your state into your measurement model. In this case, the measurement is an estimate of the state. This is, if you put this in, you get an estimate of what the state is at time n. So this is basically your estimate of the state at time n going through your measurement model, which in this case is just a multiplication by a matrix, and that gives you an estimate of your measurement. And if you look at your measurement model, if you've got a good estimate of the state, and you subtract off hn, xn from yn, then the only thing that's left is your measurement noise. And so when you're looking at this difference between your measurement and your estimated measurement, this actually has a name. It's called an innovation in the state space tracking literature. And this series of innovations should be a white noise sequence. And for those of you that took the class with me last year, you remember there's lots of different ways of characterizing a white noise process. Its autocorrelation should be an impulse. Its power spectral density should be flat. And if you look at the difference between your measurement and your estimated measurements, and you look at this process, if it has a PSD that is not white, then you're not doing a good job tracking or maybe modeling your process. Then something's wrong. And you can get clues as to what's wrong by studying that process. In general, you never know what the true state is. No, you don't usually have that, but you always have your measurements, and comparing that to your estimated measurements is a great diagnostic and tuning tool. I'll say much more about that later, but since it came up here, I wanted to mention it. So it turns out that and what ends up being the variance of that random variable is another normal distribution, and we can evaluate that PDF and treat it kind of like a likelihood function in this case when we've got a model that's in this form. Andy?
In this measurement model, are we assuming that V is Gaussian white noise, or is it just white noise?
There's a complicated answer to that, but in this particular example, and for our purposes, for all this math to work out, and for this to end up truly being normally distributed, or normal distribution, and for this ending up being a normal distribution, you need the two noise processes to be normally distributed as well. If that's not the case in your particular application, this will probably still work pretty well, but you can no longer argue that if you've got your million particles that it will converge to the true estimate, because the derivation of getting these two equations, the two key ingredients that you needed, are based on the fact that these are both normally distributed. Sorry, I know that wasn't the answer you wanted. All right, so this is great. In this particular case, for this much less general state space model, or any state space model that can be expressed in this form, additive noise and a linear measurement model, then it turns out that we can get exactly what we need with something that we can implement relatively efficiently. So that's good news. But in most cases you can't do this, but in this case you can. What was I going to say? I'm sorry. I lost my train of thought on this slide. In most cases, you can't do it. We saw an example where we could solve for the optimal importance density. Usually, you can't do it. There's a lot of approaches to trying to approximate that optimal importance function. A lot of them are iterative. A lot of them are computationally intensive and lack convergence results. But we can approximate this type of linear model directly. And that makes it better. The points I was making here, I'm sorry, I can't quite follow those. I know where I'm going with this, and it's going to make sense. So generally, we've got a parametric distribution for the importance density, and it ends up coming down to defining a finite set of parameters, such as the mean and the covariance, if you've got a normal distribution. So we can call this set of parameters theta, and it depends, but if you've got an importance density that comes down to estimating those parameters, then that makes it a little bit easier because then we just have to estimate those. And the common choice is to choose your distributions to be Gaussian. You can wave the central limit theorem flag as we often do as engineers. But that limits us to something that's unimodal and symmetric about the mean. But at least then we only have to solve for the mean and the variance of the distribution. What is often done, and what I'll show you an example of, is using this local linearization technique. And this is kind of a prelude to the extended common filter and the unscented common filter, and if we have time, what's called a Gaussian sum filter. So all three of those basically are trying to approximate nonlinear dynamics with a linear model. And so if we did, for example, if we've got the nonlinear measurement model now, we still have additive noise, which is very common. But if we have that, the nonlinear part of this, we can represent as, by a Taylor series expansion, is basically the measurement model evaluated at some estimate of the state, plus the difference between what we think the state is going to be and what it actually is, multiplied by this Jacobian. And this is not simply a partial derivative. Keep in mind, x of n is a vector, and if we basically take the derivative of this nonlinear function relative to a vector, this ends up being an entire matrix. It's not just a scalar. So, and we're evaluating this at xn equal to our best estimate of what it's going to be, basically at the nonlinear function projecting the state forward one step ahead. So if we accept this approximation, then we end up basically with a linear measurement model, and then we can apply the results from before. And many of you, in many of your applications, as I think we've seen in almost all the examples except for Waltz, we've got additive process noise and additive measurement noise. But the measurement model and the process model are both nonlinear and they can be time varying. So it fits almost all the examples that you've come up with so far. So this is called the local linearization particle filter, and this is in a form where I think you could actually code it up. And again, I know I haven't gone through all of these equations, but the main difference between the example before and this one is that now we're getting an approximation of what the we're approximating the nonlinear measurement model as a linear function, and this is where we calculate the Jacobian. And calculating Jacobians was something that was very common in the 70s when they were using the extended Kalman filter for a lot of different applications. And so if you've got a big state space model, a lot of engineering time was spent cranking through the math to figuring out what these Jacobians are, what all those partial derivatives are, because you've got a different element for each matrix, and if you get just one of them wrong, it can make the tracking go really badly. These days, even if we wanted the actual Jacobian, we could go to a symbolic math solver in MATLAB or Python or a number of different tools and just have it solve for us directly. But it used to be that a lot of time went into solving for those Jacobians so they could use something similar to this called the extended Kalman filter. So this is it. We can do this with anything that has additive process noise and additive measurement noise, which is a lot of different state space models, including the one that we looked at before with the car tracking, where we're going around the track that you're already familiar with. So in this case, we actually have a linear process model, but we've got a nonlinear measurement model. So it's kind of the opposite of what we needed for the first one that I showed you. And again, I've got all the same values that you've seen before. I'm glad you're already familiar with this example, because then we can focus on what's different in doing it this way. So if we're going to use this new technique with an approximation of the optimal importance density, then we have to go through and solve for the Jacobians. In this case, fortunately, we only have to calculate one partial derivative, but you can see it's even a bit of work in this case to go through and calculate that one partial derivative, because in this case, we've just got the one state variable. And so by the time all is said and done, we end up with this expression where the a prime and b prime are these functions that are defined up here. So this ends up being the Jacobian, or in this case, it's just a scalar, but that ends up being that linear H matrix. You guys with me? Is this okay?
At first, the theta was just your state variable in this example.
I can't go backwards.
Yeah, no, I just this first step here of restating that the Jacobian with x of n, and then in the next it's theta that is just plugged in.
The theta, the theta was the bearing angle.
Yeah.
So this was theta, but actually the state
Was the angle there.
was the position of the car on the track. So if the car is right here, and this isn't quite right because it would actually go the other way around the loop. So that angle is phi, and that's the state that we're trying to track. You know, where is the car expressed as an angle going around the circle? But the thing that we actually measure, the y, is this bearing angle plus noise. So the state really is phi, which is what this is all expressed in terms of. So I think we're good. Any other questions so far? Okay.
But don't you, the theta is in the measurement model, right? So shouldn't we be dealing with?
We had to, there's
Well,
a,
it's
there's
function
a,
of
there's
phi,
a,
yeah, okay.
yeah, it is a function.
This is
Just had to
right.
restate it as,
Right.
based on the
Exactly. This
geometry.
is a function of phi, which is what we're trying to track.
Sorry, yeah.
Any other questions? Okay. All right, so, you know, again, this is a simple case. Have some sympathy for the poor engineers of the 70s who were doing all this by hand. Thank goodness we don't have to do that anymore. It's really easy to make errors, and that's why a lot of time went into calculating these Jacobians. But I'll show you a number of different ways of avoiding that later this term. Again, these days we've got computations and symbolic math solvers, so you can plug this into MATLAB and say, give me the derivative, and give it to you, or Python, or again, any other tools. So here we go. I'm only going to use 100 particles, and you've seen this example before. This is our measurement. We're trying to estimate this from that, and again, it's impressive that you could even start doing that. This is with the same importance density that we started off with, the same one that I asked you to do the homework with, and that I've recommended to you, where Qn of x of n given as much as the past as you want of both the measurements and the state, this should be -1, ends up just being set equal to the prior. This is what all of you have been using. So we're just really feeding the particles through the process model. And so this is what you've seen before. I showed this to you when we were when I was introducing this idea of particle filters. So this is as a basis of comparison. And this gives us an idea. You've seen these plots. It's really mostly illustrating where the points where we resample. We can get really that same information, although I've drawn vertical lines in this case, showing the number of effective particles, and again, it gives you an idea of how often it has to resample. It's a moderate amount. And this is the true posterior, again with the confidence intervals for the particle, and it tracks the mean, looking at how close the green is on top of the blue. It's pretty good. And again, this is all basis of comparison. We've seen this before. So what happens when we use this new technique, which is a linearized approximation of the optimal importance density? So again, if we restrict ourselves, we're going to advance the particles forward in time and compute them recursively, and now we're using this linearized approximation. How well does it do? Well, this is what the particle trajectories look like. And I know you don't have that other slide probably in front of you, or at least I can't display it side by side quite yet. But it doesn't really look that much different.
It's a lot tighter.
Seems better.
Does it seem like it's a lot tighter?
It's a lot tighter. And it doesn't have nearly the fan out before it snaps.
I think side by side coming up. This is the resampling. So again, you can see there's still resampling. Our weights are still headed to 0. Whether they're doing it at the same rate or not is debatable. And I'll show this side by side also. And this is what how the performance changes. Now keep in mind, this is not the kernel density estimate, but this is the true optimal tracking calculation of the posterior. So you shouldn't pay any attention really to the image or the pink regions, because that's all computed optimally. What you should be looking at is the confidence intervals and how close the particle mean is to the true mean. So how close the green is to the blue, and how close the yellow is to the edges of the pink. And it's probably better. On this slide, I finally show them side by side. And I know it's hard to see on the scale. Scott, can I ask you to kill the lights? So it's hard on the screen to get them side by side, but if you look at this closely, you'll see that the prior here wasn't tracking the confidence interval as well as the optimal is. You know, so if you really care about tracking those percentiles really precisely, there is some improvement, a little bit, in using the optimal. We also see that it is tracking the true mean a little bit better with optimal. If you look at how often the green is right on top of the blue, it's a little bit closer in this region than in this region. I don't know if you can see that on the slide, but there are some differences, but it's just a smidge better, I would argue. And if we look at the resampling, how often we have to resample. Now keep in mind this is the optimal importance density. It's the thing that's supposed to minimize the variance of the weights as you go forward in time, and yet we still see the weights, dropping. And there's a little bit less resampling here. I think there were 14 resamples versus 20. So in this particular example, there was a little bit of improvement, but not a lot. And while your point may be correct that it's keeping the particles where they ought to be, I should have done a side-by-side with the particle trajectories as well, but I don't think I have that in these slides.
I think when I looked at it, it looked like in the prior importance density, they fan out a lot more quickly. So it could just be with this importance density that there's less variance over time of the particles. So they tend to stay closer to one of the previous values.
They should, since they're conditioned on the measurements. I mean, by including that measurement, you've got more information on where the particles should be, so it should be tighter. But I didn't think it was visually distinguishable, but maybe it was. And again, I'm sorry, with what I've got, I can't go backwards, at least not easily. If I hit backwards, it starts recording where I left off on that slide. Like it's got audio associated with each slide. So if I go backwards, the audio gets all screwed up. And then it's like you hear the future of the talk, and then you go forward to the next slide, and you're hearing the past. It just gets all messed up. So that's why I can add slides, but I still wouldn't be able to do them side by side. So in that particular example, and Scott, you can turn the light back on to keep us awake. In that particular example, I would argue that the improvement was marginal. We went through a lot of work. There's a lot more computation with carrying all those matrices around with each particle, rather than a particle just being a single vector, or in this case, a single scalar and a weight associated with it. Now we've got those matrices we've got to carry along as well, and there's a lot more computation involved for every particle, and yet the performance gain, I would argue, is very small in that particular example. Amit, you asked a good question of when is it good? And as I've expressed, or tried to express, if your process model gives you really good knowledge about where the state ought to be, then using that as your prior works pretty well. Using the prior for your importance density tends to work very well. This is a counterexample where it's a very simple model. It's scalar, and it's a random walk process with a huge step size. So we've got a standard deviation of 10, which means that we're taking huge steps and going from x of n to x of n plus 1. And our measurement model is simply the state plus noise. So it's a linear measurement model, and it's on the same scale in this case. But now we've got a very much less measurement noise than we have process noise. And you can't normally consider these directly because they have different units. This is in whatever the units are of your measurement, and this is in the units of your state. But in this case, they're the same because the measurement is just state plus noise. So in this case, every time we get a measurement, it gives us a really good idea of where the state is. And in this case, the process model gives us very little knowledge, or the dynamics give us very little idea. It's almost like a white noise process. So this is an example where the opposite is true. The measurements are really good, the prior knowledge is really coarse or really poor, really limited, however you want to express that. Does that make sense? Okay, so again, using the prior as the importance density, let's see what that looks like. Of course, the measurement now is on the same scale as the state, and it's really good. You can see the state's going all over the place, and even with a little bit of noise, this is a really good representation of where the state is. So our measurement gives us a lot of information about the state. And if you do a side-by-side, I did in this case, of the particle trajectories, you can see if you're using the prior, this is using, I should have labeled this. This is the prior, this is the optimal. And even from this slide alone, I think you can see what's happening. You see the particles sort of scatter out and they collapse back in. They scatter out and collapse back in. That's because it's resampling almost every time step. They get snapped back because when you advance them forward using the prior, you're putting particles in places that are very inconsistent with the measurements you have. And the measurements are so good, a lot of those particles immediately end up having their weights just go to zero, and you drop below your effective particle threshold, and it hits the resampling. Whereas with the optimal, you don't see that effect. It's doing a really good job because it's optimal, and in this case, our measurements are really good. And if you look at the estimates, this is unimodal, of course, because everything is linear. So we've got a unimodal posterior. But, when I look at these two, I can't really see the difference between them. And it's arguably, maybe I made the measurement model too good in this case. But when you're arguing about the benefit, you resample much less frequently. But at the end of the day, what you're really trying to track is some property of the posterior, such as the mean, or the median, or the mode, or something like that. And both of these do a beautiful job of tracking that. And it's my experience with these and thinking through as best I can this idea of the optimal importance density that is touted so highly in the books and in the literature and the tutorials, that led me to conclude there isn't really probably in many cases that much to be gained. You may have to resample a lot and maybe things aren't quite as good, but you're burning a lot less computation per particle when you're using the prior than you are when you're using the optimal. And yet the performance gain for even keeping the number of particles constant, where you're really using a lot more computation for the optimal, it doesn't seem like at the end of the day like you really gain that much. The resampling is heuristic and maybe none of us like it, but it seems to work really well. And I've got limited experience, but I don't really see the big benefits of the optimal importance density. I know in your reading it says this is a really important decision. To me, it seems like it's less important than a lot of other decisions that you have to make. Although don't use the uniform.
Yeah,
That's taking it too far.
In this case, because it's a linear process and a linear model, we could just use a Kalman filter, and that would also be helpful.
Yeah, right. And you're absolutely right. If you've got a linear state space model, even if it's time varying, like use the Kalman filter and you're done. As long as you're interested in tracking the mean, even if you don't have Gaussian noise, it turns out. That's why I hesitated with your earlier question. The Kalman filter is still optimal if you're estimating the mean, even if your additive noise is not Gaussian. I'll state the optimality criterion later when we talk about the Kalman filter. But so yeah, you're right. And I was trying to tip things in favor of the optimal importance density by making it linear. It really is optimal. There's no linear approximation that I was using in this case. Like, it's as good as it gets. And yet, it's still, because we're moving the particles forward, the number of effective particles is still going to drop. You're still going to have to do resampling. You haven't gotten rid of resampling. In this case, where it's really tilted in favor of this, it only resampled once here, where it resampled 161 times with a prior, which is a lot. When you're only looking at 250 samples. That's an average of almost every other, more than every other sample, more frequently than every other sample. But it still tracked really well. Like, the resampling was not that big of a problem, I would argue. at least in this example, and a lot less computation. So in summary, we would like to sample from the posterior. Like this would be definitely the optimal thing to do. We can't do it. This is not something we can do recursively. It's sort of the new thing. I don't have that on the slides, but that's, I think, the kind of the fundamental limitation. One of the first limitations of this is we can't do that. So if you're going to limit yourself to recursively generating the particles where you're advancing them forward in time, then it turns out that this is as good as you're going to do. It minimizes the variance of the weights. In fact, it gets it down to 0. This is what most people mean when they're talking about an optimal importance density, is they're really talking about, well, you're going to be doing it recursively. If you're going to do it recursively, then that's it. That's the thing you want. But you usually can't sample from it. If we use a local linear approximation, then you can sort of solve for the, now it's in quotation marks, because you're getting the optimal importance density for an approximation of your state space process. And so, all the convergence results are gone because it's only a local linear approximation. But still, people do it. People have been using linear approximations for decades with these things. And with the linear approximation is usually better than the prior. This is using the prior. This is with a linear, you can get something that is an approximation of the optimal importance density. Oh, you know what? And I have to correct something I just said. The asymptotic theoretical results still hold, even if you're not sampling from the optimal importance density, as long as you know what it is that you're sampling from, and you can evaluate the weight update exactly, then you're okay. But that's where you would lose it. I don't have that equation on this slide, but remember the weight update was W of n is equal to W of n minus 1 times P of, it's kind of like the likelihood, but it was conditioned on x of n minus 1. And there is no problem with sampling from an approximation of whatever the optimal importance density is. But then when you're doing the weight update, we had a cancellation assuming that was exact, which would no longer be true. And this approximation would no longer be exactly true if you're using a linear approximation. So that's where the convergence results, the asymptotic results, would break down. But in any case, in practice, the results are going to vary. It's best when your linear approximation is accurate, so don't do what Ethan did. The local linear approximation, when you've got that severe kind of measurement nonlinear or process nonlinearity, is going to cause problems. You can't get a good local linear approximation when you have something that looks like that.
But didn't we talk about how that the linear approximation is of the measurement, not of the process update?
Yes, you're right. Thank you, Andy. You're absolutely right. So if you had something like that in your measurement model, then you wouldn't want to do it. But it was in the process model, so he probably would have been okay. You're right. You're right. Thank you. But the linear approximation requires a heck of a lot more computation, especially when you're not dealing with the one-dimensional case. And we'll talk about a better way of doing linearization a little bit later in the term. But bottom line, based on my limited experience with these particle filters, in most applications, the prior is a good choice. And especially if you can optimize your code to get 1 million particles, it usually isn't worth the computation and the effort to try to get this linear approximation of the optimal. And if you're not going to do it that way, I don't know how else you can do it. There are some other particle filtering techniques that try to address some of these same problems. But when it comes to picking your importance density, I stand by, based on my experience so far, and supervising students using these in projects, it seems to me that the prior has always worked pretty well, with the resampling, of course. Yeah?
If we defined optimality by the sense how close it is to the Bayesian posterior, instead of just minimizing the variance of weights.
So you want to talk about how close your estimate of the PDF of the density is.
Right.
And keep in mind, this is trickier than what you're led to believe based on the examples, because we've all been working in the one-dimensional case.
Yeah.
I mean, in general, that PDF is impulses in a multi-dimensional space because your state vector has multiple dimensions. And if you're talking about how good is this approximation with these impulses, a multi-dimensional PDF to the actual posterior, the marginal posterior, that becomes a hard thing to quantify.
Right. An easier thing would be comparing the mean of the PDF and the mean of the particles.
Except
You don't have the PDF.
well, there's that,
Yeah.
but also the particle filters really shine when you've got a multimodal PDF.
Yeah.
If you've got a multimodal PDF, you usually don't want to be tracking the mean. The mean's usually a bad choice if it's multimodal. We've seen a lot of examples, even from some of the state space models you guys have cooked up, where it's multimodal and the mean is nowhere near a mode.
Yeah. Again, so what's the motivation behind minimizing the variance of weights apart from infrequent resampling?
That's it, isn't it?
That's it.
I think all
Well,
those things are just
There's
directly related.
there's a lot of good things. One of the issues that I haven't talked about much yet is particle diversity. Every time you resample, you collapse all your particles to just a few places in the state space. And now you're blind to the regions where particles are not located. And if you're in a very high dimensional space, you may say, well, I mean, the counter argument would be, well, those are improbable places anyway. I don't want particles there. They're going to have small weights, and why would I want them there? But if you're in a high dimensional space with a lot of different modes all over the place, even if you've got a million particles, it can be you can end up not having modes covered. And as soon as you lose a mode, it's very hard to recover it down the road. And the resampling pulls the particles away from those modes. So it's far better if you can to not be resampling when you're in a high dimensional space. But it seems to me this optimal importance density, one, you usually can't do it. At best, you can only approximate it. When you do approximate it, you've now got much more computation. And it seems to me that there's still, even then, you don't gain that much. The weights are still going to head to zero. They may head to zero more slowly, but you're still going to have to resample. So why go through all that work and wasted computation when you could spin that on particles, do less math, and have less risk of getting the Jacobian wrong and screwing everything up?
Okay. The example we had in the measurement model, we have the noise was very small, right? The variance of the noise. If we took another example where that noise was a lot higher than the process noise, would it still be the optimal? I mean, should it still be the optimal importance density? But the same intuition doesn't hold.
It's still optimal, but now it's not much different than just using the prior.
That's true, right? Yeah. Right.
So once again,
Right.
just
Yeah, of course.
just use the prior.
Right.
Is my thought.
Yeah.
It seems like it has most of its use case when you have that nonlinear prior and then the linear, close to linear observations.
Yeah.
Then it seems like there'd be more of a benefit there because you're able to take advantage. With the prior, you just don't include any of the information about the measurements.
Yeah, that's right. We haven't talked much about the process of state space model design, but usually I think you'll find in most applications, including the examples you guys have been bringing out in your homework, the nonlinearities are often in the measurement model and not so much in the process dynamics. I guess you guys both had nonlinearities in your process dynamics, you as well as the measurement model, but often they're in how the measurements relate to the state is where the kind of nasty nonlinearities are. So, and that's not the good case, that's not the one where this optimal technique works well.
So when you were talking about linearizing the measurement model, then you can look at the error between the real measurement and your predicted.
Yeah.
Which made me think of like LMS and made me wonder, can you use that error signal somehow, feed it back into a particle filter?
Yeah.
You're like
Some of you took that.
each time step, or?
Some of you took that class on adaptive filters, and I believe the common filter was introduced then as a way of doing adaptive filtering. At least that's what I've done. So the best estimate of the state at time n given n under the common filter recursions in the linear filter framework turns out to be the predicted value from the process model plus the common gain, which turns out to be optimal, times exactly this difference. So your intuition that this error may be a useful thing to feed back to update our state is spot on. It's exactly right, and there turns out to be an optimal way to do it. But this is kind of the naive estimate, just advancing your estimate of the state forward one time step into the future based on your process model. And then the way that you incorporate your measurement is actually by taking a difference between what the measurement really is and what you predicted it would be based on this estimate of the state. So, yeah, you're absolutely right. And it turns out, though, that rather than doing some kind of feedback, the common filter is already accounting for that in this exact equation with the famous common filter gain with this matrix right here. So more to be said about that, but the medium length answer is yes, or the short answer is yes, for the reasons I stated. Any other questions before we break? Okay, well, if you think of more, we can cover those again on Thursday, but I think we'll probably move on to what's called auxiliary particle filters, which is another way of doing this. It's kind of a more elegant way of accounting for the measurements. It's nice. So I'll see you then.